Thank you. Yeah, first of all, thank you very much to the organizers for inviting me. It's a great honor. My name is Teresa. I'm a PhD student at IST Austria, or actually I should say ISTA, because we had a name change recently, and we also got a new logo. This is joint work with my supervisor, Herbert Edelsbrunner, and a master student that we co-supervised together, Jyamiti, and Dmitry Morozov is also involved, but not so much in what I will present today, more in the future work section. Okay, so let's start with some motivation and all the definitions. Then I will talk about the main topic, the periodic merge tree, and in the end, I will give you some outlook on future work. Let's dive right in with a motivating application. Namely, in this paper by Dmitry Morozov and his co-authors, they tried to predict how good different nanoporous materials are in removing methane from the air. And that is, for this, they realized that the whole structure is important, which is not surprising because you want to find out whether the methane molecule can get stuck in the whole structure. By the way, I should say here, removing methane from air is relevant because it's a greenhouse gas, so you really want to remove it. And for this computing of the whole structure, they wanted to compute persistent homology. They could have also decided for the merge tree, or for maybe more relevant for the whole structure is actually the merge tree of the complement. I will talk a bit about that later. But anyway, they wanted to compute persistent homology, but they had a problem, namely persistent homology is not defined for crystalline materials. It might sound weird now, but you will later see why. And so they found some workaround solution and it worked for them. They were able to improve the state of the art, which is great. But Dmitry asked me if I can do some research in that direction to maybe even improve that method. This is what we'll do now. However, I will do it for the periodic merge tree, which you can also see as a first step towards persistent homology, because the merge tree is basically zero-dimensional persistent homology. First, I will define all the words in the title. First of all, these crystalline materials that I talked about, we model them by modeling the center of every atom by a point, and then you get a periodic point set. This is just a point set that is invariant under three linearly independent translations. And if it's, I should say, you can only see here two, but the third one you should imagine coming out of the screen. And in general, my pictures will be in 2D, but think of them as three-dimensional because crystals live in three-dimensional space. And if it's invariant under those three translations, then it's also invariant under all sums of them. So it's invariant under a whole lattice of translation spanned by those three vectors. But those periodic point sets are infinite, which makes sense because if you can translate it once, you can also translate it infinitely often. So you have to have infinitely many points. And nobody wants an infinite point set as an input for anything. So we need to use a finite representation, which is just a tile that you can cut out such that repeating this tile infinitely often in all directions yields back the periodic point set. And so then this tile, we call it the unit cell, is a parallel epiped spanned by three vectors, v1, v2, v3. And the finite point set inside we call the motif. And so our finite representation are those three vectors and this finite point set. And that's really exactly the input that the chemists give us when they send us a material. So you should think of a periodic point set as an equivalence class of finite representations, where you can see they can look very different from each other, but we still want that no matter which finite representation you choose today, you should get the same output every time. And for that periodic point set, from that periodic point set, you can construct periodic filtration, namely, for example, the periodic alpha filtration, which is then again invariant under the same three independent translations. And for this talk, it's actually not important whether it's the alpha filtration or some other periodic filtration. So you could use any periodic function f, and then its sublevel set, and that would also give you a periodic filtration. Then another word that appears in the title is the merge tree. So let's define that. The precise definition is at the bottom, but you don't really need to read it. The important part is just that for every filtration value R, the merge tree tells you how many components there are in the sublevel set at level R. So in this case, the sublevel set has 4 different components, and the merge tree tells you this not only for one threshold, but also for how those components merge when you change the threshold. And I like to draw merge trees in such a way that if you just remove the horizontal lines, you get exactly the 0-dimensional persistent homology barcode. Okay, so much about the merge tree. The goal is now to compute or to define, first of all, the merge tree of a periodic filtration. So the merge tree of a periodic filtration is just an infinitely large object. It has infinitely many branches. Which you can see here, there's, for example, infinitely many branches here that merge into less infinitely many, but still infinitely many. So this is a very annoying object to work with. You don't want to have an infinitely large object as the output of your computation. So what we want is some kind of summary of this. And so now, spoiler alert, I'm already kind of showing you the solution here. We want some kind of finite merge tree with some decoration, namely those many parallel little branches. We can call them twigs, and then we can bundle infinitely many of those twigs into branches. And then we want to only plot the finitely many branches and the information of how many infinitely many branches they contain. So you will see later more about this. But before, when we looked at this application, I told you that Dmitry was standing in front of this problem of wanting to compute persistent homology of a crystalline material, which is an infinite periodic point set, and persistent homology is not defined for infinite periodic point sets. If we had decided to compute a merge tree, it would be defined for infinite periodic point sets, but it's infinitely large, so not really useful. So he was standing in front of that problem, and he solved it by just taking a finite chunk and then computing persistent homology of this finite point set. But this has some problems, namely, for example, the boundary cuts through the pattern in an annoying way. So for example, that point here that I marked is now, because of that boundary, dying by merging to this other point there. So you will have a branch in the merge tree of that red length. Or if you prefer persistent homology, you will have a bar in the persistent barcode of that length. But that's just the boundary effect, because if it was perfectly nicely infinitely periodic, then this point would not get matched here. It would instead, like this point does, get matched with the point above it. And so that would be a shorter bar. And so this red bar should not exist. It's a branch that is just there because of the unwanted boundary effect, and it would not be there in the infinite periodic setting. Okay, so that's clearly a problem. So we need a different approach. If you would think about it for 10 minutes, probably what you would come up with is, let's just compute the merge tree of the finite representation, but let's identify the opposite boundaries with each other to form a torus, and we can compute the merge tree of the torus. So that sounds like a good solution, right? And hopefully it would somehow inform us about the infinite periodic filtration. But I would say it does not inform us enough. So let's take this example here where you have 2 different finite point sets in a torus. They have exactly the same merge tree on the torus, but that's a problem because they behave different in the infinite periodic setting. Namely, one of them repeats in 3 space dimension and the other one repeats in 2 space direction. So what I mean by that is, in one direction, you get actually the same component. So you get only distinct copies of that component, in the two other space directions. So again, I'm talking in 3D here. And so that means that the component on the top has infinitely many distinct copies, but somehow more infinitely many distinct copies than the component on the bottom, which also has infinitely many distinct copies. So we want to quantify this. And that's what we will do. Whoops, going the wrong direction. That's what we will do with the periodic merge tree. First, I'll just explain it in pictures. We said we could compute the merge tree just on the torus. But every branch of the torus corresponds to infinitely many twigs in the infinite periodic setting. We want to quantify how many. So we do that by looking within a finite window. So that's the ball of radius r here. And we look at this, just this finite part of space. And actually now, small detail, we don't just compute the merge tree of this finite point set. Instead, we want to, because this would have the following problem, namely that there would be components that might look like two separate components, although they actually merge with each other outside of the ball. So we still would want to count something like this just as one component, because it's one component of the infinite periodic setting that intersects this ball at least once. So we want to count it just once. But that's a detail. Basically, the idea is we want to count the components that intersect a ball of radius r. And then we look at how r changes. And so this way we get those nice numbers here. Actually, I'm cheating here a bit because I should always carry with me this constant here and this lower order term, but I'm too lazy to do that. There's also not enough space in this slide to always write this. So that's why I just left them out. It's anyway always the same. Also note that there are some parts that are cubic, quadratic, linear, and constant. So we can color them in 4 different shades of gray, which kind of denotes these 4 different eras, the cubic era, the quadratic area, and so on. And now that we have found out how many parallel twigs there always are, we don't need to draw all of them. We can just draw one branch and decorate each branch by how many twigs it corresponds to. And the eras that I talked about before, the cubic era is the phase where a connected component is not yet connected to its periodic translates. So still lots of like cubically many individual copies. Whereas the quadratic era, there you already have a connection in one direction. And so you only have distinct copies in the other 2 space dimensions. So you only have quadratically many distinct copies, and so on. Now the formal definition. We first fix a filtration value so that you just have one simplicial complex, and then only later we will talk about filtrations of such simplicial complexes. The thing that we first have to compute is the periodicity lattice of a component C, which is the lattice, which is a sublattice of the lattice lambda, under which the component is periodic. So we have all these translates of lambda, which map the component to a periodic copy, and some of them map to the exactly same periodic copy, and some of them map to a distinct copy. And this is useful because we want to count the number of distinct copies. And so we can do that by counting the number of all copies and then modding out the copies that give actually the very same component. Okay, but this number is still infinite. And we said we want to quantify how infinite this is. By the way, this is very related to this paper by Adam Onus and Vanessa Robbins, but one of the key differences between our work and their work is that they basically stop here and say, okay, the answer is infinity, and we want to continue and quantify how infinite the answer is. And the good thing is we have reduced the problem to just quantifying how big the quotient of two lattices is. We can completely forget about the fact that this has something to do with homology and so on. We found those two lattices, and now we want to quantify how big their quotient is. And we have a theorem for that. Namely, we can just look at any pair of lattices, and we want to quantify how big the quotient is. And again, we do that by intersecting with a ball of radius r to make it finite. We only count equivalence classes of this lattice quotient within the ball of radius r. And then the formula looks complicated, but the important parts about this formula are it only depends on the pair of lattices. So in particular, lambda is usually given, so it only depends on the lattice lambda 0. So once we can compute that, we can just evaluate this formula. Namely, it depends on the dimension of the lattice lambda 0, it's this p here, and it depends on the volume that the basis elements of lambda 0 span. And then, so that's the first term is an important number that we will have to compute. The next term is just a constant. Oops. Then we have a monomial plus a lower order term. And this I call the copy monomial because it counts the copies, and it's a monomial. And this should look familiar to you because that's exactly this copy monomial that I showed you before. And so you can already see, I can not only do this for every fixed filtration value, I can do that for the whole, for every filtration value. And this way I can decorate the whole merge tree of the torus. And this has been implemented by our master student, Chiara. And I will show you now how she implemented it. So again, we first fix a filtration step and just do it for that fixed simplicial, periodic simplicial complex. Later we can then do it for filtrations. We only need the vertices and edges because we're only interested in the merge tree, so in zero homology. So that's enough here. Then we choose one connected component for which we now want to compute the periodicity lattice lambda c. Remember, once we have computed lambda c, it's just plugging into that formula and we get the copy monomial. So to compute this, we look, and I should say the periodicity lattice, if you already forgot, it's this lattice under which the component is periodic. So to compute this now, we look at the graph on the torus. We orient the edges arbitrarily. And we label every of those oriented edges by a so-called crossing vector, which just states which boundaries it crosses. So all the gray edges, they don't cross any boundaries. So I label them with 0, 0, 0. The blue vector crosses the boundary in the y direction. So that's why it gets 0, 1, 0. And if there was, for example, such a green vector which crosses in the x direction, then it would get to the vector 1, 0, 0. Just that you understand how these crossing vectors are calculated. I need a bit more space, so I shifted this up because we continue now. Namely by computing the one homology, just as if the edges were unoriented. So we get those three cycles. And we can choose an arbitrary cycle representative basis. And then for each cycle in the basis, we orient the cycle. Then we sum the crossing vectors along the oriented edges of the cycle. So for those two gray cycles, we get vectors 0, 0, 0, which makes sense because they don't cross any boundaries. And for the blue cycle, when we sum over all the edges, we also sum over this one blue edge. And therefore we get 0, 1, 0 as the crossing vector of that cycle. And then we just multiply those vectors by some matrix which does a change of basis. It's not so important, but it means that in this case, we get the vector v2. And then the span of those vectors, v2, 0, and 0 in our case, yields the periodicity lattice lambda c. Let's go back to that slide that we already had before. And we can see here nicely that that's really exactly the periodicity lattice that we wanted to compute. It's periodic in that direction V2 and it all in the direction of all of its multiples, but not in the other directions. And we have a theorem that says that this algorithm indeed yields the periodicity lattice. Let me think if I have time for the proof. Let's maybe skip it for now. I would like to have lots of time for questions. So if one of you has a question about the proof, then we can of course go for the proof. But that was just about one specific slice of the filtration, so one fixed simplicial complex. Now, if you have a whole filtration of simplicial complexes, you have to first compute the merge tree on the torus. Then you compute persistent one homology. And for every birth of a one cycle, you first look in which connected component is this birth, so in which part of the merge tree. And then we know that the lattice lambda, the periodicity lattice might change from before that to after that, because we saw before the periodicity lattice is constructed by those one homology basis elements. And here the one homology changes, so the periodicity lattice might change. Namely, if it was before spanned by some vectors u1, u2, then it's now spanned by u1, u2, and by the crossing vector of that new cycle that is just born. Even if u1 and u2 are a lattice basis, adding this third vector might mean that it's not a lattice basis anymore. And so we have to reduce it to get again a lattice basis. And this step was actually surprisingly difficult. We thought there must be some literature about this, but we didn't really find anything. So we came up with our own approach how to do this, and Chiara implemented it also. It was a lot of work for Chiara. And yeah, so I'm really curious if someone of you has maybe a better idea how to do this. So if you know anything about this, please let me know. How to reduce a lattice basis. Okay, a few lattice vectors that do not form a basis. How do you reduce that into a basis? Okay, and then I told you that once we have all the periodicity lattices, we just plug it into the formula of the copy monomial, and then we get all the copy monomials. And that's already the whole periodic merge tree. Now, some words about future work. There are two different directions of future work. One of them is, we already talked about defined and computed the periodic merge trees themselves, but it would also be interesting to define and compute distances between them. And that would have one advantage, namely with those distances, we could then also show nice properties about the periodic merge tree. Namely, I of course defined the periodic merge tree already in a way such that I know it will have nice properties. So what I mean by this is that the bigger picture here is that you would want to find the periodic merge tree together with a distance function, or actually it will be a pseudo distance. So pseudo just means that different points can also, or different, in this case, periodic merge trees can also get value 0 assigned. And the periodic merge tree part we already have. We already have a function that maps periodic filtrations to finite merge trees because we don't want infinite objects with decorations. And the pseudo distance I'm currently in the process of writing down, and then also writing down those proofs for those nice properties that we want. Namely, one of them is invariance and the choice of finite representation. We said before that we can choose different representations for the same periodic point set, but we want that the answer is the same. Actually, the periodic merge trees won't be exactly the same, but we want that they at least get distance 0 assigned. Then we also want stability, which just means that if I perturb my points by at most epsilon, I want that the merge tree also changes by at most epsilon. And it's important because I can perturb also only every second of the hearts. The other half I leave unperturbed. And this forces me to take this larger unit cell. And so this also explains why the invariance property is so important. I can only get stability if I get invariance. Then we already mentioned before, we don't want any branches that just come due to boundary effects. All the branches, so zero homology bars that we get, we want them to be the same as in the infinite tree, just with different multiplicities, namely finite multiplicities. And we want it, of course, to be computable, which I already demonstrated to you. And there is a completely different direction of future work, namely to extend this to higher dimensions. That would then be persistent homology instead of merge tree. Here, just a few words. We have this, in zero homology, we have the advantage of canonical generators, which we don't have in one homology. Namely, the pair of pans shows any two of those free cycles form a basis, and it's not clear which one you should choose. And I can also make a periodic pair of pans. And this periodic pair of pans causes lots of troubles when you want to generalize this to higher dimensions. But what you can do is you can compute the merge tree of the complement. And this gives you information about two homology, because two homology is simply the cubic error of the merge tree, periodic merge tree of the complement. Namely, if a component of the complement is not yet connected to its periodic copies, then that means that it's enclosed by a void. Whereas the quadratic error of the periodic merge tree of the complement corresponds to such voids that are connected to its neighbors, so they don't form closed voids anymore. Instead, they form an infinitely long tunnel. So that gives you some information about one homology. And then the linear and constant error basically give you information about systems of tunnels. And you can therefore compute the periodic merge tree, the periodic merge tree of the complement. There's one more thing that I can compute, which I won't go into detail now. And it seemed to us at first it might already capture everything, but it actually doesn't. So there's still future work to do how to define persistent homology in higher dimensions to actually capture everything. Here are just some important papers that we cite. And thank you very much for your attention.
Any question there? Sure.
Yeah, very nice talk, Teresa. On a couple of your slides, you had a V sub 3 or this coefficient or new 3. Can you tell us more about that?
So what kind of tree did I have?
There was a coefficient briefly on your slides.
Yeah, I know what you mean. Yeah, that was in the definition part.
Yes.
Yeah. So that's just the volume of the 3 minus p dimensional ball of radius 1.
I see. Did you also consider the case where you might have something, two features repeating kind of in the same dimension count, but one of them twice as often as the other?
Yes. Yeah, that brings up a good point that maybe if we look here, those numbers are quite interesting. They're not just something like r cubed, r squared. They can also be the square root of 2 times r squared or something like this. And that depends, for example, if you have one of those quadratic features, so connected in one direction, it can be connected in different ways. And one particularly exciting way how it can be connected is that it doesn't connect directly to its neighbor on the right, but rather to its neighbor 2 to the right. So it only connects the even points with each other. And then the odds are also connected to each other, but even and odd are not connected with each other. So that's, for example, one interesting way how you can have a multiplicity that is exactly twice as often as the multiplicity of something else. Or the square root of 2 can happen if you have connections not exactly vertical, not exactly vertical, not exactly horizontal, but diagonally, because there are more parallel diagonal lines than there are parallel exactly vertical lines. That's maybe not so easy to understand now, but it is like that. So yeah, they're non-trivial. This constant is trivial, but that coefficient, that is completely non-trivial. So that really has something to do with how this lambda 0 is connecting the different periodic copies.
Thank you. Very cool.
We can have one more question.
There's one in the chat.
Oh,
So Dong Chen asks how to select the initial point cloud to analyze for real crystalline compounds.
Yeah, so I'm not a chemist, so I guess I'm maybe the wrong person to really answer this. But I think the idea is also that the chemists would give you just lots of point clouds, and for each of them you would compute the whole structure. And then if you have one where you see that the whole structure is particularly good, then maybe you want to explore more similar materials. So you go back to the chemist, and the chemist gives you then some new materials. It would be probably some back and forth with the chemist. So I don't know in that application where Dmitry was working on how exactly they got their data set, but I think it was just the chemists gave it to them.
yeah, thank you. So we can set up for the second part.